Welcome back to the deep dive. So today we're looking at a piece of engineering that is, it's honestly punching way above its weight class.
Way above.
We've got the technical docs for the ISS360 and ISS360 HD imaging sonars from Impact Subsea. And when I say weight class, I mean that literally. This thing is what, 0.37 kilograms?
It's tiny.
Yeah.
I mean, it's just unbelievably small. And, usually in underwater acoustics, tiny often means toy.
Right, a glorified fish finder.
Exactly. You expect low range, low resolution. But looking at the specs here, Impact Subsea has somehow crammed world-class imaging into a body the size of a soda can.
Which is the mission for this deep dive, right? How did they pull that off? And it seems like the secret sauce really starts with the signal itself. If you look at older mechanical sonars, they all rely on that single frequency pulse, and that creates this huge bottleneck with something called range resolution.
That is the big hurdle, yeah. Range resolution is basically just the ability to tell that two objects are actually two distinct objects.
And not just one big blurry blob.
Exactly. And in a standard system, that resolution is tied strictly to the pulse length. So a typical setup might only distinguish objects if they're, about 150 millimeters apart?
Which is roughly 6 inches. That's fine if you're looking for a shipwreck, I guess, but it's a total disaster if you're trying to, manipulate a valve with an ROV arm.
Or inspect for hairline cracks. Yeah, precisely. So the ISS360 it ditches that single tone. It uses CHRP technology.
Compressed high-intensity radar pulse.
Right. And instead of just hitting one note, it sweeps across this massive bandwidth from 600 all the way to 900 kilohertz.
It's like instead of hitting one key on a piano, the sonar just slides its finger across the whole upper register.
That's a great analogy, actually. And because it has that sweep, the processing can sharpen the image, drastically. We go from that 150 millimeter blur
down to 2.5 millimeters.
2.5 millimeters. That is the main takeaway right there. You are getting nearly photographic detail, seeing individual chain syncs solely because of that CHRP bandwidth.
And it solves another massive headache, right? The noise.
Oh, yeah. They implemented what they call the Impact Subsea Signaling Scheme, or IS cubed. It uses phase modulation.
Yeah.
So basically, if you have 5 of these things working in a swarm, their sonars won't blind each other.
They can just tune out everyone else's noise.
Exactly.
Which is a perfect segue into, the actual operation, because clarity is one thing, but mechanical sonars are they're agonizingly slow historically.
That classic radar sweep effect, yeah.
You're waiting for the head to physically spin ping by ping.
It's usually the Achilles heel. But looking at the benchmarks here, the ISS360 is clocking scan speeds up to 6 times faster than comparable units, especially at short ranges.
So is that just a faster motor? Or is there more going on under the hood?
It's the processing. It's all in the processing. It uses a digital correlation technique with, and this is key, zero data filtering. It's just crunching the raw acoustic data right there internally and shooting it over Ethernet instantly.
And that's crucial because it moves the device from being just for imaging to being for navigation.
Right. At that speed, you can actually use it for obstacle avoidance on a moving vehicle. You don't need to bolt on a separate, heavy multi-beam sonar just to keep from crashing into a wall.
It simplifies the entire payload.
Immensely. You've got one sensor doing the job of 2.
Okay, so let's talk about the hardware itself. Salt water. It just destroys electronics. And normally, manufacturers use anodized aluminum, which is fine, I guess.
It's fine until you scratch it.
And then the pitting starts.
Exactly. So Impact Subsea, just skip that entirely. The housing is solid titanium. It's effectively immune to the environment. But the part that really stood out to me is the inductively coupled transducer.
The solution to the slip ring problem, right?
It is. In a mechanical sonar, that head has to spin 360 degrees constantly. Traditionally, you use physical slip rings to keep that electrical connection.
Which are just contact points. They use friction, they wear out.
They wear out, they fail. It's a major point of failure. So by using inductive coupling, they're transferring power and data magnetically. There's no physical contact at all.
No friction points.
Zero. You could theoretically spin that head for 10 years straight, and the connection quality wouldn't degrade. For a long-term deployment, that's a game changer.
And it really seems like they're targeting the autonomous market pretty hard with this. I noticed they have their Seaview V3 software, but they also just threw the SDK up on GitHub.
And that is the final piece of the puzzle, isn't it? By making the integration open source, they aren't just selling you a camera. They are selling a core sensor for autonomous robots.
Right. So developers can integrate this directly into their vehicle's control loop. So let's put it all together for you. You have a titanium unit that doesn't corrode. It has no slip rings that can wear out. It sees with millimeter precision using GRP, and it's fast enough for a robot to actually drive itself.
It really feels like the hardware has finally caught up to the software.
Yeah.
We have been talking about autonomous underwater swarms for years, but the sensors were always too big or too slow.
Which leaves us with a thought to chew on. If you have sensors that are this small, this durable, and they don't interfere with each other, are we finally looking at the infrastructure that makes large-scale, collaborative underwater drone swarms a reality?
The barrier to entry just got a lot lower.
Something to watch for sure. Thanks for diving in with us.
It's my pleasure.
Catch you on the next one.